People are still joining. Okay, but let us start because we cannot wait for. Okay, presentation. Can you see the slides? Oh, just a minute.
Sir.
Okay, so let's start from where we left in the previous class. So I will just go with a fast recapitulation of what we have discussed in the previous class. So we applied the boundary conditions at the interface of two linear medium, and we have seen that if we agree with this phase matching condition, then that enforces the law of reflection and law of refraction that is known to us already. And if you also apply the boundary conditions to this, I mean at the boundary, then we have this set of Fresnel equations by solving which we can get the amplitude of the reflected and transmitted electric field in terms of the amplitude of the incident electric field. And then we discussed about this alpha and beta in these Fresnel's equations. So we saw that if alpha is 1, that corresponds to the case of a normal incidence. So we get back the equation that we have derived earlier. And also there is another case for which if the incident angle is 90 degree, then alpha diverges, and you can see that the entire light is reflected. So the so the entire light is reflected, and there is nearly no transmitted component. We can also have another case where alpha equal to beta, that corresponds to some incident angle of incidence, which we call theta b, or the Brewster's angle. And if you take that to be the case, that theta equal to theta b for alpha equal to beta, for which E0R will be 0, then you can find out the value of theta b in terms of the refractive index of the two medium. So we derived that. So tan theta b equal to n2 by n1 is a well-known Brewster's law for polarization in the plane of incidence. So we have talked about this in the previous class, and as it states that if you are in the plane of, the electric field is in the plane of incidence, then if the angle of incidence is theta b, then the light will not be reflected. So there will be no reflected component. And if it is unpolarized light, then we will have a perfectly polarized reflected component. And why? We have discussed it in the previous class, so I'm not repeating that again because we are short of time. And then we have to calculate the reflectance or the reflection coefficient or the transmission coefficient for the case of oblique incidence. So let us see. So what do we mean by intensity? Intensity is the energy crossing per unit area per unit time, right? We have already discussed this in the case of normal incidence, for which the value of this intensity for the incident electromagnetic wave was half epsilon 1 v1 E0 I square. But there is an extra cos theta I factor here. Why? So let us go back to the picture to make it clear. If you look at this picture, so light is now incident at an angle theta I, right? This angle is theta I. So imagine now a cylinder which is centered on this incident ray, cylinder with cross section of, say, unity, so unit area. And if the area is unity, when it intersects with the boundary, of course the area which will cut at the boundary will not be unity. That will be unity times cos theta I, right? So we are right now talking about the energy per unit area per. So that's why this cos theta I factor is there. And similarly, the same kind of cosine factor will be present for the reflected and the transmitted radiation. And if we take a ratio of those intensity of the reflected to incident, and then we'll get a reflection coefficient. And if we take the ratio of the transmitted intensity to the incident intensity, then we'll get the transmission coefficient. So you can easily simplify this because you already know what is the cos theta y, cos theta I, because cos theta r by cos theta I, since theta r equal to theta I, so this will be cancelled. It's just a minute. So since theta I equal to theta r, so naturally this Gauss factor will be not be there in the ratio. And if you calculate the transmission coefficient, this theta t by theta I is against n2 by n1, sorry, n1 by n2. So you can plug that in here, and you can simplify that to obtain the relation. So r equal to alpha minus beta divided by alpha plus beta square, and t equal to alpha beta times 2 by alpha plus beta square. So okay, these similar kind of expression we have obtained for normal incidence where alpha equal to 1. And you see there is only one difference here, that is the angle is not normal here, it is oblique angle. And then if you sum these two numbers, that is reflection coefficient and transmitted coefficient, of course you expect it to be 1. If you add this number and add this expression with this expression, you will get 1. And that is natural because energy is conserved, right? Whatever light is being incident will partly uh, so what I actually I will request you, please try to join within 5 minutes, right? Otherwise, I mean, things get delayed, and then we'll not be able to cover what we intend to complete within this class time, right? So please join in time. Okay.
Okay.
So okay, so this r plus t equal to, okay, oh, thank you. So r plus t will be 1 because energy will be conserved. Whatever light has been incident on the interface, it will be partly reflected and partly transmitted. So if you add them up, the amount of energy which is reflected and transmitted must be equal to the I mean incident energy. So that is the energy conservation law. Oh wait, so now this is a very simplified version of the entire physical process. But you see, I have not told you that what exactly happening at the interface. We have Maxwell's equation, and that provides us a set of boundary conditions which we are applying at the boundary, and obtain the final equation, and then calculated what should be the fraction of energy that will be reflected, and what will be the fraction of energy that will be transmitted. But you see, this any medium is basically made up of say atoms, or say molecules, dipoles. So I mean, unless you have a clear picture what it is made up of, it is difficult to exactly understand what is happening at the interface. Because if you go to the microscopic picture, you see there are let me just give you example, because here we are dealing with the classical electromagnetic theory, and we do not have any scope of going into quantum mechanics here. So you see, I mean, whenever light is incident, light is electromagnetic wave, and that carries energy and momentum. And when it is imparted on some surface, that surface is made up of some I mean, it is some material which have, I mean, a distinct value of permittivity, permeability, density, and so on. So you see, if I ask you a simple question, you see, if you look at a block of wood, I mean, it is not very
Hello, hello, sir. Hello,
স্যার আমরা শুনতে পাচ্ছি না।
hello.
Hello, sir. We can't hear you, sir. Hello.
Yeah, I can hear you. And can someone answer whether you are able to hear me or not?
Hi, sir.
Yes, sir. Now we can hear you, sir.
Now it's audible.
ওকে ফাইন ঠিক আছে তাহলে আমরা যেখানে আলোচনা করছিলাম লেট মি জাস্ট ওকে পিপল আর স্টিল জয়নিং ওকে क्या হলো কি হলো এটা প্রেজেন্টেশন মোডে যায় সো যেটা আমরা আলোচনা করছিলাম যে if you take a piece of metal the surface is different, right? It's a metal. Okay, maybe it's not. Suppose you take another surface. So I just gave you an example of metal because I am going to discuss about conductor right now. So what is happening if you have a lot of free electrons at the surface? The light electromagnetic wave will interact with the free electrons because electric field আছে incoming electromagnetic wave tar, so it will act on the free electrons and they will oscillate, free charges on the surface of the metal, so they're oscillating. If they oscillate, we'll learn in this course that oscillating dipoles can actually give rise to electromagnetic radiation. So what is happening actually, they are actually re-radiating, and that's why the metal surface is shining.
স্যার প্রেজেন্টেশনটা দেখা যাচ্ছে
স্যার প্রেজেন্টেশন দেখা যাচ্ছে না।
দেখা যাচ্ছে না স্ক্রিনটা?
না স্যার
আচ্ছা আচ্ছা, আমি ক্রস করে আবার করছি, আমার ওয়েট আবার করছি, আবার ক্রস করে একটু ওয়েট করো। What happened? Let me see. Okay. Now no, I don't want this. Can you see now? Hello?
হ্যাঁ স্যার দেখা যাচ্ছে।
আচ্ছা ঠিক আছে, সবাই দেখতে পাচ্ছ?
হ্যাঁ স্যার।
ওকে ওকে ঠিক আছে, ঠিক আছে। তাহলে যেটা আমরা আলোচনা করছিলাম যে এটা আমরা আলোচনা জাস্ট ব্রিফলি টাচ করলাম এখানে, বিকজ ইউ সি when light passes through glass বেশিরভাগ লাইটে পাস করে যাচ্ছে কেন, why, right? So for that, to understand that, you have to understand the structure of glass, because the energy levels of glass may not match with the incoming electromagnetic radiation, and it may allow to pass it through. That's why it is transparent, but a block of wood is not, right? Because wood is the constituent atoms are interacting with electromagnetic radiation, it's absorbing that. And suppose I mean it's a simple example, these are now x-ray, optical light যেন গায়ে এসে পড়ে আমাদের বডি ট্রান্সপারেন্ট নয়, তাই না? It will block the light, but if you shine x-ray it will pass through. So it depends on the frequency of the incoming electromagnetic wave, and it interacts with the medium. And that's why in some cases you get more light to be reflected, and in some cases less light to be reflected. So of course, I mean this is not this is not the point of my discussion, because it is not part of the classical electromagnetic theory. I just mentioned it so that you have the idea why in some cases you have more reflected light, in some cases you have less reflected light, and so on. Okay, now let us move on to conductors, because we have very less amount of time in this semester, so we have to try to wrap up this recapitulation part as soon as possible. Okay, so let us now move into conductors. So what do you mean with conductors? Of course, we have discussed about the propagation of electromagnetic waves in vacuum and in linear homogeneous medium like in a dielectric and so on. So the only difference, remember, the only difference here is basically the metals or the conductors, they contain a lot of free charge density, and consequently they can have also free current density, because if you have free charges they can move around and give I know. Actually, I understand. Actually, many of you may have been facing problems with the signal. But what I will request that please try to join within 5 minutes, because I mean, if I it breaks the flow of the discussion, right? Because if I have to keep on adding people, I mean, after every 2 minutes or 3 minutes, it becomes very distracting, right? It destroys the flow of the discussion. So I understand some of you are having some problems with the signals. Maybe you are getting disconnected and are trying to do this. So that is fine. But if it is only a couple of times, that is fine. But if it is happening again and again and again, then it's basically it's difficult to complete the discussion, right? So you have to be also responsible. Fine. So in conductors, we have free charge density, and I mean, as I told you, free charge density can give rise to free current density, and this simply also this is known to us, Ohm's law. We have learned that two different versions, V equal to IR, which can be also recast in this form, where the current density is proportional to the electric field, and this is the relationship between applied electric field and the free current density. And let us see how the Maxwell's equations get modified in conductors, right? So you see, this is the first law, that is the Gauss's law. Divergence of E is equal to rho free by epsilon. Epsilon is the permittivity of the metal. This is the free charge density. Of course, the second equation, there is nothing to change, because this is you can close your eyes and believe on this. Divergence of B equal to 0 everywhere. Okay, that is related to the non-existence of magnetic monopoles. So you don't have to think about it. A curl of E will be minus del V del T. Faraday's law. And the fourth one, the modified Ampere's law, you see there are two terms. The first term was this mu times the current density. The second term was mu times epsilon times del E del T. And in this case, see, in case of dielectric or vacuum, we had 0. The first term was 0, because there were no free charges, so there were no current density, so that term was 0. Right, but here now we have free charges, and naturally we have a current density corresponding to that those charges, which again, if you write mu into J free, and J free is sigma E, so I just put this sigma E in place of J free. So these are the four Maxwell's equations in conductors. Now let us see where it leads us to. So we want to now try to understand how do I figure out the form of the electromagnetic wave that will propagate inside a conductor, right? We have now two extra numbers here, rho free and J free, which were not present in case of vacuum or dielectric. So we have to deal with this extra complicacy here. So let us see. Now you see, when charge flows from one region to other, charge, I mean, is conserved. You know it. It's from the equation of continuity, right? So you have the J dot and dA equal to basically dq dt minus dot del q del t. So suppose a volume contains an amount of charge q and it's bounded by a surface S. So if the charges are coming in or flowing out from that volume, they must be conserved, right? So the flux of basically the charge in this current density J dot and dA has to be equal to the rate of change of the charge inside that volume. And if we apply simply divergence theorem, that gives us the divergence of J is equal to Q is rho d, basically dV. So we are basically dropping the integral over dV from both sides. So we have minus del rho del T. This is well-known equation of continuity, which demands the conservation of charges. Now you see, once you start with this equation, because you have free charges in metal and they can flow from one place to other, giving rise to current, and that's why we need this equation. And if we combine this with the first equation, that is the Gauss's law, divergence of E equal to rho free by epsilon. So you see, I am simply putting here sigma times E, because in the previous slide I showed you the Ohm's law, JF equal to sigma E. So I am just putting here sigma into E. So sigma is a constant which will come out. So divergence of E, and divergence of E is rho free by epsilon now. So if I use that, we have an equation like this: del rho F del T equal to minus sigma by epsilon rho free. And you can, you can write del rho F by rho F equal to minus of sigma by epsilon into del T. And if you integrate that, you get a solution for the free charge density, which is a function of time. So rho free as a function of time is rho 0 times exponential of minus of sigma divided by epsilon times T. So sigma and epsilon are the property of the conductor or the metal, so it's a constant. So it's a function of exponential decay of charge, free charges. It's saying that the free charge density will decay with time. Now, how fast? That depends on the value of sigma and epsilon. You see, you can recast this again as minus of t by tau. So you can see this tau is nothing but epsilon by sigma. And this value of tau actually decides how fast the free charge density will decay in a particular metal. Right now, you see this tau. What is the significance of tau? So tau is basically, it's called a relaxation time. So what is relaxation time? It is the time over which any free charge density in conductor dissipates by a factor of 1 by E, that is 0.367 times the original charge density in that this conductor, roughly 1/3 of the value that we start with. So tau is the time over which the free charge density in conductor dissipates by a factor of 1 by E, that is 1/3 roughly. And you see, based on the value of tau, one can classify conductors into good one and bad one. So you can classify conductors as good conductors or bad conductors. So what are good conductors and bad conductors? You see, to understand this, let us go back to the fourth equation, Maxwell's equation, right? How do we define good conductor and bad conductor? Probably you remember my discussion from the first class. I told you why displacement current was not measurable by all the experimental physicists who were working on electricity and magnetism. I told you that E itself contains E0 cos omega t, that will throw away an omega terms outside this, and omega by c square, mu epsilon is c square, in this case it will be v square. So if unless this omega is comparable, or maybe you don't need a comparable value, but if omega is very, very small as compared to the velocity square of that of the electromagnetic wave in that medium, this will be very negligible. So you cannot really detect this one. You see, now you look at these two terms. So there are two different types of current density. One is the free current density, another is displacement current density. So if you compare between these two terms, then it will tell you how good the conductor is. So for a good conductor, you see the free current density should be much larger than the displacement current density. If you take a ratio of this, you see del del t will lead you to E0 cos omega t, so mu epsilon omega cos omega t, and this is mu sigma E0 cos omega t. I mean, I am taking the real part, E0 to the power I omega t, so I am just taking the real part. So mu sigma E0 to the power I omega t, this will be mu epsilon omega E0 cos omega t. Right? So if you take a ratio of these two terms, that will tell you whether the conductor is good or bad. You see, here I have written sigma by epsilon omega. Take the ratio. It will be evident. See, mu gets cancelled. Mu gets cancelled. Sigma, and there is omega term coming out from this time derivative. So sigma divided by epsilon omega is the quantity which is of importance here. So sigma, so that is telling you that with the conduction current and the displacement current, if you take the ratio between the two, that comes out to be sigma by epsilon omega. And if it is very larger than 1, then you decide that this conductor is a good conductor, right? And you see, naturally, if sigma by epsilon omega is much greater than 1, then what happens? How did we define tau? You see, look at tau. Tau is epsilon by sigma. Now come here. Epsilon by sigma, right? So one can define tau, right? So we have already defined tau, epsilon by sigma. So that means, see, what is omega? Omega is basically related to a characteristic time of the electromagnetic wave, because so it has a wavelength, and you know t equal to 2 pi by omega, so that this omega corresponds to the time period, right? This is a frequency, although it's a frequency, so the inverse of omega corresponds to some time, the characteristic time of the wave, which is basically what we have considered in this case. Now you see the dissipation time. If the dissipation time is much shorter than this characteristic time of the wave, then it's a good conductor, because the free charge density dissipates very fast, right? On the other hand, if you take a bad conductor, naturally the ratio of conduction current and displacement current will be much shorter than 1. So sigma by epsilon omega will be much shorter than 1. So in that case, you see the dissipation time is much larger than the characteristic time associated with the wave or the whatever electric field that we are talking about. So omega inverse is a time, right, which is associated with the variation of the amplitude of the electromagnetic signal or the electric field here. variation with electric field. So naturally, if the time period of dissipation of the free charge density is very large as compared to the characteristic time of the wave, then it is called bad conductor. So just remember the definition. This is the criteria for a good conductor, and this is the criteria for a bad conductor, right? It is entirely based on the these two things. One is the ratio of conduction current and displacement current, and the relaxation time. Fine. Okay. So now let's move ahead. And okay, I should also mention that for a perfect conductor, of course, this is an idealized case. You should not believe it. Sigma equal to infinity, right? So it's infinity if it is infinity, because it's of course I am not talking about superconductor. It's a perfect conductors. So sigma equal to infinity. That means sigma equal to infinity. How do we define? And this is tau. Tau is epsilon by sigma, right? And sigma infinity means tau 0. That means within no time the free charge density becomes 0. But of course this looks odd. I mean, you cannot talk like this. Then no time. Okay, it may be some time, with very short time. So that means what it is telling us, that if you take a very good conductor, the free charge density within the conductor will dissipate very fast. What will happen? Where will the charge go? Will they evaporate? No, of course not. They will not evaporate. What will happen? They will dissipate from the volume of the metal. I mean, suppose you take a wire which is containing a lot of free electron inside it. So what will happen? Because of the Maxwell's equation, they will immediately dissipate from the volume and go to the surface. Now you see, there is no such thing like mathematical surface again, because we always idealize things like that, surface and volume and so on. Because so what it is telling you, that the free charges will be mostly contained on the surface of the metal, not inside the volume. They will dissipate very fast because of the continuity equation and Maxwell's equation, and that is the thing that we should keep in mind while dealing with conductors. Okay, so now how do we modify the first equation? Because divergence of E was rho free by epsilon. If you remember the equation that we started with, you see this was the case, divergence of E equal to rho free. But rho free 0, it will dissipate. That is what equation of continuity tells us in case of metal. So then this equation gets modified, and we have divergence of E equal to 0, right? And divergence of B is 0 all the time. Curl of E equal to minus del B del T. Curl of B equal to mu sigma times the electric field plus mu epsilon del E del T. Now we have this 4 Maxwell's equation, and we have to analyze the situation in a similar manner, just as we did it for vacuum or linear medium. So what was the approach? We took curl of E and we take curl of this equation, third equation on both sides, and curl of this equation on both sides. So if you do that, it's simple. You just take curl of E, then you just plug in, because you know already curl of B. So you plug in this value here and simplify. That will simply give you these two equations for E and B. And note the difference carefully. You see, if the conductor suppose has zero conductivity. Of course, conductor cannot have zero conductivity. But what I'm saying, suppose this term is not there. You see, if this term is not there, then everything boils down to the things which you have discussed earlier, right? If then sigma is 0, then it's naturally this wave equation, plain wave equation in basically vacuum or sorry, linear medium, because mu and epsilon are not mu naught and epsilon naught. So once sigma is 0, they are nothing but this plain wave equations in linear material. But since sigma is there, we have this extra term over there. So this is again a wave equation, of course not the same kind of that we obtained for a linear material or vacuum, with this additional term which is there, and for that we have to understand what actually exactly the physical meaning of it. What are the consequences of this term, because there is this term. So let us start with a very simple discussion, so I'm not making things complicated. Of course, this kind of equations can be solved in different ways. So here, let us try with a trial solution, the same kind of solution that we have dealt with in the case of a vacuum or say linear medium. Here I have written EZT just to indicate that the electromagnetic wave is propagating along the Z direction and the electric field is polarized along X direction, right? And we could have taken ERT, R vector T, and EI k dot r vector r minus omega t, but I have not written that because just to make things simple so that you understand everything, because as soon as I make the directions arbitrary, I mean it becomes a bit difficult to visualize things, right? So this is a very simple picture where the electromagnetic wave is propagating along z direction, the electric field is polarized along x direction, and it is incident on some metal, right? So that is sorry, we are actually discussing about the propagation of electromagnetic wave in the metal. So we have this equation, we have assumed this solution inside metal. So now if you plug in this solution in these two equations, let us take the first equation. I mean, they will be similar, right? Here I am talking about the electric field. So let us plug in this solution inside the first equation. So it's literally e to the power I kz minus omega t. So this is the spatial part, this is the time part. So there is a Laplacian here. So naturally it will throw out a k square term, and since there is a del 2 del t2, so it will throw out a omega square term. I mean minus I omega, so minus plus and then I square, and since there is a del E del T term, so it will throw out I omega term, right? So if you put all those factors minus Laplacian of E del E del T and del 2 E del T2, this will give you equation like this. It's quite straightforward. You can just plug in that equation and you get this, right? Just k square equal to I mu sigma omega mu epsilon omega. So what is the difference? Again, I'm emphasizing the difference so that things becomes clear to you. You see, if there is no sigma, this term is not there, right? If this term is not there, what is k? K is square root of mu epsilon omega. That is the natural dispersion relation in case of say linear material, right? Because this mu epsilon is nothing but related to the velocity. So omega equal to basically omega relationship between omega k and v. That is a well-known relationship. But since in this case conductivity is not zero, it's a conductor, so there is this imaginary term sitting over there, right? And this has some importance because this dispersion relation is telling you that the presence of an imaginary term in sigma, and this tells us that the relationship, the dispersion relation between that is the relationship between k and omega is a bit more complicated than what we have discussed in vacuum or in case of any material. So what is the difference? You can literally see that k, this again I should tell you that k is a vector here, but again here since I am writing k, amplitude of k is k square, that's why I have not written in vector, because k dot k is k square, so I am not writing k dot k as a vector form. This is just amplitude of k, and this tells you that the k must have to have two different components. That means it is telling you that k is a complex quantity. It should have a real part as well as an imaginary part because of this presence of this term, that is mu sigma omega. So k is this is the most striking difference. The wave vector in a conductor becomes complex. It's a complex quantity. It is a real part and an imaginary part. So let us try to understand the physical significance of these two different components, the real part and the imaginary part. So here I am labeling the real part as kr and imaginary part as ki. Okay, so I should remind you that ki is not imaginary. Ki I am just labeling the imaginary part to be ki because it is clubbed with this I. So that's why I am calling it the imaginary part of the wave vector, and I am label it as ki. So only ki are the real part. Now we would like to separate these parts and try to see what do they actually tell us. How do we separate them? You see, simply if I put k equal to kr plus I ki here in this equation and then simplify and then equate the real part from both sides and imaginary part from both sides, then we will get two equations. Just to put this k equal to kr plus I ki on the left hand side of this, square it and equate the real part and imaginary part from both sides. That will give us two equations. If you basically equate the imaginary part, that will give you a relationship like that. That is relationship between ki and kr in term ki comes in terms of kr mu sigma omega by 2 kr. Okay, it's quite straightforward. So since because I cannot write down all the steps in the slides, so if you have any difficulty, I can send you the calculations. Right, it's straightforward. Okay, and if you equate the real parts, that will give you this equation. Now you see, this second equation is a quadratic equation in kr square, right? So if I write kr to the power 4 as kr square, then ax square minus plus bx plus c, right? And if you just look at the values of a, b, c, you can find out the solution. A is 1 here, b is minus mu epsilon omega square, and c is minus of mu sigma omega by 2 whole square. So if you take the value, if you just note down the value of a, b, and c, and write down what is the solution. Solution is here kr square. So kr square is just as usual minus b plus minus root over b square minus 4ac by 2a. And if you simplify that, you will get basically plus minus. So basically you have to choose one of them. So this is a kr. By solving this quadratic equation, you can get this kr. And if you put this kr in this equation here over there, then you get ki. So the real component and real part and imaginary part of the wave vector can be easily obtained from this quadratic equation, and combining that solution with this equation, right? And what are the physical meaning of these two terms, that is real terms and the imaginary terms, that we have to understand. Because you see, once we write k equal to kr plus I ky, okay, let us again go to the solution that we have started with. So this is electric field, plane wave, electric field of a plane wave, which has this complex amplitude, right? Because it contains the power I delta term. It is polarized. It is polarization along the x direction, and it is propagating along the z direction. This is standard expression, so I have not written anything new here. B can be obtained by just taking a cross product of the unit vector of the unit wave vector with this E. So k cap cross E by V will give you the magnetic field of the electromagnetic wave. So now we have seen that the wave vector k is a complex quantity. It has a real and imaginary part. So if we plug in this into these two equations, what do we get? You see, EZT now becomes E0 tilde e to the power minus of Kij. Remember, Ki is not a complex quantity. It's a number, right? It's some number, Ki, right? Ki into Z into e to the power I krz minus omega t. You see, this part is the usual plane wave thing, which you have already encountered in vacuum or any material, linear material. This is the new part here is e to the power minus Kij. And what this tells you, that this amplitude of the electric field will exponentially get damped. It will get damped by exponentially because of the presence of this e to the power minus ki z term in this expression. So what is ki? We have already obtained the expression for ki in a particular conductor, and ki depends on the conductivity, permeability, and the permittivity of the medium, right? So okay, so here we are trying to define a skin depth, because you can see that the electric field amplitude will decay as the electromagnetic wave propagates inside the conductor. So based on this fact, we are defining a quantity called skin depth, right? So what is skin depth? Skin depth, because of the presence of the exponential factor, we define it this way: the distance over which the amplitude of the electric field is reduced by a factor of 1 by E, that is roughly 0.367 times the original, is called the skin depth of the conductor. And this basically measures how far the electromagnetic wave can penetrate inside the conductor, right? So electromagnetic wave inside conductor gets damped away. The amplitude changes as it propagates through the conductor. It decays away, and how fast it decays away, that depends on the value of the skin depth, right? And you see, skin depth, as you have defined, skin depth is naturally 1 by ki because of this factor e to the power minus kij. So if I write minus z by delta I, when z equal to delta I, E becomes E0 by E, small e. So I can write e to the power minus z by delta, where delta equal to 1 by ki, and this delta is called skin depth. Since we have already obtained the expression for the imaginary part of the wave vector, we can simply put it here and analyze the situation. So this is the skin depth delta for any conductor, and you see the presence of the terms, right? Omega, mu, epsilon, and so on. I should also remind you, see the real part of the wave vector, which is this one, kr, right? Kr also depends on these things, right? You see, kr also depends on the frequency. So the wave vector or the wavelength depends on the frequency. It's not the frequency and also the conductivity of the medium. Frequency is natural, of course, conductivity of the medium. So which I am not discussing right now. So we are discussing about the skin depth here. So skin depth is telling us that this should be the expression for the skin depth of the permittivity and permeability of the medium. The skin depth may have different values. Now, what was the criteria for a good conductor? If you remember, sigma by epsilon omega, that has to be much greater than 1. That was the criteria for a good conductor, right? So then you can just simply take that condition inside this, right? Sigma by epsilon omega is much greater than 1, so you can drop this term and simplify it straightforward. You will get a value of ki. Of course, delta is inverse of ki. You can simplify ki directly this one as well, and no, doesn't matter actually. So ki for a good conductor is square root of mu sigma omega by 2, right? So it's linearly proportional to the permeability, conductivity, and the frequency of the electric field. And naturally, delta comes out to be square root of 2 by mu sigma omega, right? So the skin depth for a good conductor is 2 by mu sigma omega. Okay, fine. What about so what is the physical significance of it? That we have to understand. I mean, it has several applications in real life, right? Because I may just give you a couple of examples. Okay, let me just first finish this discussion for bad conductor as well. So if you take a bad conductor, then sigma by epsilon omega is much less than 1, and you see ki can be written as sigma by 2 square root of mu by epsilon, and naturally delta will be inverse of that. Now what is the difference between this and that from a good conductor and bad conductor? You see, for a good conductor, skin depth depends on frequency, whereas for a bad conductor it is completely independent of omega. It doesn't depend on frequency. Now I will give you a couple of examples. One example is simply you may be aware of that for power transmission we use copper wires, right? Copper wires. Why? What is the why should we prefer copper wires? Because you see, irons, if you take copper, of course you may argue with me that copper has a higher conductivity, right? Because so what do you want? A skin depth to be larger or larger delta? Well, smaller delta means faster attenuation, higher power loss. So what do you want? In order to minimize power loss, when you are transmitting power from one place to other, you should also take into account the amount of power that you are going to lose during the transmission process, right? So the amount of transmission can be minimized by increasing delta. So if you enlarge delta, makes the delta larger, then of course your power loss will be lesser. But how do you ensure that? You see, okay, for copper, so for copper, I told you that already, that conductivity of copper, this conductivity of copper is I think roughly 6 times the conductivity of iron, right? So if I take a iron wire and a copper wire and compare between the two, who should have a larger delta for a given frequency? Let us take the frequency of the kind of frequency that we use in our day-to-day life in home appliances in our home. That is around 60 hertz. Suppose 60 hertz is the frequency, and if you put here omega corresponding to 60 hertz, and as say sigma, I tell you the sigma of copper is 6 times higher than the sigma of iron, right? So you should not then use copper, right? Or you should use copper. There are two competing factors which you should remember here, mu and sigma, right? Because mu is permeability and it is known that the mu value of mu in iron is much larger than the mu of copper, right? Mu in iron is much larger than the mu of copper, whereas sigma of iron is a bit smaller, right, than copper. 6 times conductivity of copper is 6 times the conductivity of iron. So if you put the values here, I am just telling you the numbers here. So if you use 60 Hertz and take a copper wire, the skin depth in case of copper will come out about 8.61 millimeter, and in case of iron it will be 0.65 millimeter. So you see, for iron it is much lesser. The skin depth is very small, 0.65 mm, and in copper it is 8.61 mm. So the power loss in case of copper wire will be lesser as compared to the iron wire. And this is important. Suppose you are carrying power from here to Delhi, right? So you may wonder that copper is a very costly wire, why should I use copper? But if you calculate the cost over, say, 5 years, your power loss will be a very important factor in this, because you will lose a lot of money for that, right? So that's why copper wire is preferred over iron wire, and this is entirely based on the skin depth of the metal that we are using for propagation of electromagnetic signal, right? In case of conductor or a current carrying wire, the electric field is along the wire, right? Applied electric field. And magnetic field, you know, if you for a current carrying wire, what is the direction of magnetic field? They are coaxial, these circular rings, right? E and B, right? And they carry energy. We'll come to that when we discuss about the pointing vector. So not right now. So skin depth has a lot of importance. Other than this, I can also tell you another example that comes from another example from warfare. I mean, you know, submarines are used in warfare, right? So submarines are basically the kind of things that are used under the sea, and in order to communicate with the submarine, you need to send an electromagnetic signal. So if you send an electromagnetic signal, see why the skin depth is important here, because the sea water has a very high conductivity, because it is sodium chloride, right? Sodium and chloride is ionized, so sea water is highly conducting, and it has a conductivity of around 5 ohm inverse, 5 mho. It's called mho, 5 mho, and permeability around actually 1 value. You can take the permeability to be 1. Conductivity is 5 mho, and if that is the case, then it depends how far your signal can penetrate inside the sea based on the frequency that you are using. You see, because skin depth depends on mu, sigma, and omega. So sea water has a well-defined value of sigma, that is 5 mho, right? Mu is 1. Now the skin depth entirely depends on omega, the kind of radio signal you are using here. Why you should use radio? Because you want to, you see here, you want to minimize delta or maximize delta. In the previous case, you see here, these two things are different, right? In the previous case also you wanted a bigger delta. Here also you want a bigger delta. Why? Because you want the electromagnetic signal which you are trying to use to communicate with the submarine should be penetrating deeper in the sea, so that you can actually receive the signal while remaining at a deeper part of the sea. Whereas if the skin depth is very small, say 1 feet, then you have to come near the surface in order to receive that signal, and that is very dangerous, right? Because if you are coming near the surface, the submarine comes near the surface, it can be tracked by enemies and destroyed by a torpedo. So it is very important to have a bigger skin depth, and to get a bigger skin depth, you see, you have to lower the frequency. Lower the frequency means higher the wavelength. So extremely low frequency radio waves are needed in order to efficiently communicate with the submarine. Extremely low frequency means extremely larger wavelength. Radio signal, radio waves are basically waves with omega less than around 10 power 9 hertz. So basically, let us take one example. Say I'm talking about radio wave of 1 megahertz frequency that corresponds to a wavelength of around 2 kilometer. And if you use that here, your delta comes out to be 0.2 meter. That is very small. right? If you use a 1 megahertz radio signal to communicate with the submarine, the delta value is around 0.2 meter, that is 20 centimeter. You have to come almost near the surface in order to receive the signal, right, from your boss. It is very difficult. And if you want to really have a efficient communication with lesser danger or lesser risk, you have to have a lower frequency electromagnetic radio signal, right? So it is a very active area of research, how to generate extremely low frequency radio waves, right? It is a very difficult task. It's not so easy, as I am saying, because you see, if I tell you one example, you will understand. If I have a 1 kilohertz radio signal that corresponds to wavelength of 2000 kilometers, so you can understand an electromagnetic wave spanning 2000 kilometers, right? Right. And for that case, you will have delta value, a skin depth of around 7 meter, right? So, okay, reasonable. At least you can come up to the 7 meter depth from the surface and receive the signal safely, right? So that's why this skin depth is very important. If you consider the propagation of electromagnetic wave, or if you are trying to communicate, then this skin depth is very important. Let me just give you another example. I don't know whether you have noted it or not. If you are inside an elevator or a metallic chamber, you weak, and that is because of this, because the electromagnetic waves gets attenuated, right? So this is the direction along which the wave is propagating, and this is the amplitude of the electric field, and you can see that the amplitude gradually decays away as it penetrates inside the conductor, and how fast it gets attenuated or decays away, that depends on the type of conductor you have, conductivity and kind of electromagnetic wave that you are using. That is the frequency of the wave, right? And so this is the delta over which the amplitude is roughly 1/3 of the original, and this is called the skin depth of the conductor. And this is another cartoon picture, because electromagnetic wave in air and amplitude is same, it is not changing, but as soon as it encounters a conductor, the amplitude gradually decays away, right? It decays, right? And that is the effect of this attenuation, and it gets attenuated. Now, if I ask you what is the physical region, okay, I have a solution which is telling me that the amplitude will decay away, but there must be some kind of physical region behind it. Why it is getting attenuated? Why the amplitude decreases? The region is very simple. You see, any conductor contains a lot of free electrons, whether it's a sea surface or a copper wire or an iron wire. It carries a lot of free electron. In that case, in sea water, it is ions basically, because sodium and chloride is an ion. I'm not talking about electrons. So free charges. And when electric field is incident, an electromagnetic wave is incident on a surface which contains a lot of free charges, again, what will happen? This incident electric field will apply force on the free charges, and these free charges will move around. So there can be some kind of free current due to the motion of the charges. Of course, it may not be coherent, but there will be some kind of sort of current. And since the electrons are moving around on the surface, they will generate heat. And this heat, basically this dissipation of energy in the form of heat, will basically carrying out energy from the incoming electromagnetic wave. So it is taking away energy from the incoming electromagnetic wave, and that's why the amplitude of the electric field will get dissipated and or decrease. It will decrease as it goes inside the conductor, right? So this is the simple. হ্যাঁ বলছি, যখন একটা ইলেকট্রোম্যাগনেটিক ওয়েভ একটা কন্ডাক্টর এসে পড়ে, তখন যেটা হয় যে we have oscillating electric field, right, and oscillating magnetic field. এই oscillating electric field যখন ফ্রি চার্জের উপর এসে পড়বে, তখন ফ্রি চার্জ গুলো নড়াচড়া করবে, মুভ করবে। তাহলে চার্জ মুভ করা মানে কারেন্ট, তাই তো? তো চার্জ যদি মুভ করে, তার মানে চার্জটার ভিতরে কেউ কাজ করছে। কে কাজ করছে? ইলেকট্রিক ফিল্ডটা কাজ করছে। তার মানে সেই যে কাজ করছে, তার মানে ইনকামিং ইলেকট্রিক ফিল্ডটা কাজ করছে বলে কিছু এনার্জি খরচা হবে। এবার যে ইলেকট্রনটা নড়াচড়া করছে, তার জন্য কি হবে? কলিশন হবে, কারেন্ট গেলে কি হয়? হিটিং হয়, আমরা জানি। তার মানে মেটেরিয়ালটা যেখানে ইলেকট্রিক ফিল্ডটা এসে পড়েছে, সেটা কি হবে? হিটেড হবে। আর হিটেড হওয়া মানে তার মানে ইনকামিং ইলেকট্রোম্যাগনেটিক ওয়েভটা থেকে এনার্জি ইন দ্য ফর্ম অফ হিট ডিসিপেটেড হয়ে যাচ্ছে, যে কারণে স্ট্রেংথ অফ ইলেকট্রিক ফিল্ডটা আস্তে আস্তে কমে যাচ্ছে। যেই এটা ভেতরে ঢোকার চেষ্টা করছে মেটেরিয়ালের মধ্যে, আস্তে আস্তে অ্যাম্প্লিটিউডটা ডিকে করছে। ফিজিক্যালি এটাই হচ্ছে। আমরা সলিউশন পেলাম, ঠিক আছে, একটা কিছু বলছে আমাদেরকে কমে যাবে, কিন্তু কেন কমে যাবে? তার কারণটা হচ্ছে এই যে ফ্রি ইলেকট্রনস আছে, হ্যাঁ, এখন কতটা ফ্রি ইলেকট্রনস আছে তার উপর ডিপেন্ড। কন্ডাক্টিভিটি মানে কি, ডিপেন্ডস অন দ্য রেজিস্টিভিটি, কন্ডাক্টিভিটি আর আই মিন দ্য কানেক্টেড থিং। সো কন্ডাক্টিভিটি মোর কন্ডাক্টিং মিন্স মোর ফ্রি ইলেকট্রনস। সো বেসিক্যালি কন্ডাক্টিভিটি দিয়ে ডিসাইডেড হচ্ছে এটা, এবং কতটা দূর পর্যন্ত এটা পেনিট্রেট করতে পারবে সেটা ডিপেন্ড করছে মেটালটার উপরে। গুড কন্ডাক্টর ক্ষেত্রে আমরা সিগমাটা দিয়ে ডিসাইড করবো যে কত দূর পর্যন্ত এটা পেনিট্রেট করতে পারবে, রাইট? সো I have just given you a brief overview of the propagation of electromagnetic waves in conductors. Now there are other things, like if I ask you what is the ratio of amplitude of electric field and magnetic field in conductor, are they in phase as they were in vacuum? The answer is no. There will be a phase difference between electric field and magnetic field. Why? To understand that, you have to calculate those things. So maybe I will discuss that in the next class. So because we do not have much time left, yeah, it's almost over. So we'll discuss that in the next class. And also you can calculate the Poynting vector amount of energy that is carried out by the electromagnetic wave inside metals. And also we will discuss a bit about the propagation of electromagnetic waves, say between two conductors, or say maybe dielectric and conductor. And then we'll finish our discussion, right? So let us plan. I'm planning to start our discussion on relativistic electrodynamics from the next week onwards, right? So I will try to finish the discussion on this propagation of EM waves in conductor by the next class. Okay, so if you have any question, please ask.
স্যার এই জায়গাটার জন্য কোন বইয়ে ঠিক পাবো, মানে ঠিকঠাক করে যে আপনি যেগুলো বললেন এক্সাম্পল টাইপ?
আচ্ছা আচ্ছা, দেখো এক্সাম্পল ওগুলো তোমাকে মানে কোনো বইয়ে একদম সব রেডিমেড এক্সাম্পল ওগুলো দিয়ে বোঝানো নেই। হ্যাঁ, এগুলো বিভিন্ন জায়গা থেকে তোমাকে তুমি যদি নিজে সার্চ করো, পড়াশোনা করো, তুমি পেয়ে যাবে। কিন্তু আমি যেটা আলোচনা করছি এটা খুব সিম্পল, মানে এটা তুমি গ্রিফিথের বইটা থেকে পেয়ে যাবে। এখানে তোমাকে জ্যাকসনও যেতে হবে না, রাইট? কারণ উই আর জাস্ট রাইট নাও ডিসকাসিং অ্যাবাউট দ্য সলিউশনস অফ বেসিক্যালি ম্যাক্সওয়েলস ইকুয়েশন। তো আমি যেটা আলোচনা করছি এই ক্যালকুলেশন হয়তো স্টেপ, গ্রিফিথের বইটা খুব সোজা, তুমি গ্রিফিথের বই থেকে দেখতে পারো। আমি লাস্ট যে কটা ক্লাস আলোচনা করেছি বা হ্যাঁ গ্রিফিথের বইটা সাফিসিয়েন্ট। তবে হ্যাঁ, যে রিলেটিভিস্টিক ইলেকট্রোডাইনামিক্স অনওয়ার্ডস আমরা গ্রিফিথের বই ইউজ করবো না। হ্যাঁ, তো সেখানে আমি যে বইগুলো লাগবে আমি আগে ক্লাসে বলে দিয়েছি। আমি আবার বলে দিচ্ছি যে তোমার ওই রিলেটিভিস্টিক ইলেকট্রোডাইনামিক্স পার্টটা আমি রেজনিক থেকে রিলেটিভিটি পার্টটা পড়াই, আর সুচ যেটা জেনারেল রিলেটিভিটি ফার্স্ট কোর্স ইন জেনারেল রিলেটিভিটি তার ফার্স্ট 2 চ্যাপ্টার থেকে পড়াই। মানে আমি এগেইন বলছি, দেখো ইট ইজ সিনথেসিস অফ অল দিস থিংস, ইটস নট লাইক লাইন বাই লাইন কোনো জায়গা থেকে পড়াচ্ছি। সুতরাং সেটা বললে সেটা ভুয়া বলা হবে এবং তুমিও হতাশ হবে, কারণ তুমি যদি বলে হুবহু যেটা আমি যেভাবে বলে যাচ্ছি সেটা হুবহু কোনো বই একদম পরপর আছে, সেটা পাওয়া যাবে না। বিকজ আই এম রিডিং এ কাপল অফ বুক and then basically I'm presenting it in my own way. So basically this is kind of synthesis, and radiation part গুলো আমি জ্যাকসন থেকে পড়াই, মানে যেটা তোমার ক্লাসিক্যাল ইলেকট্রোডাইনামিক্স জ্যাকসন।
ওকে স্যার।
আচ্ছা, ঠিক আছে। Any other question? Okay, if not then fine, we will meet in the next class. আচ্ছা, আরেকটা জিনিস বলে রাখি আমি, যে আমি অলরেডি এটা বলেছিলাম যে 2 ঘন্টার ক্লাসের ব্যাপারটা আমি বলেছি, এবং যেটা আলোচনা হয়েছে এখনো পর্যন্ত রুটিনটা ফাইনালাইজ হয়নি, এটা আরো চেঞ্জ হবে। হ্যাঁ, এবং আমি রিকোয়েস্ট করেছি এটাকে ব্রেক করে দিতে, এখনো করেনি, পরে করবে আর কি। হ্যাঁ, করলে হয়তো উইদিন এ উইক অর মেবি 2 উইক জানিয়ে দেওয়া হবে যে ক্লাসটা কবে হবে। আপাতত যা আছে আমি তাই নিচ্ছি, ঠিক আছে? মেবি তোমার যদি বলো 1.5 ঘন্টা, 2 ঘন্টার জায়গায় 1.5 ঘন্টা নেওয়া যেতে পারে। পরে যখন ক্লাসটা ব্রেক করে দেবে তখন আমরা আলাদা 1 ঘন্টা করে নেবো, ঠিক আছে?
ওকে স্যার।
ওকে ওকে ওকে, বাই দেন।